small introduction to Katona. This talk, as far as I understand, continues a long strike for external combinatories and sets. So, welcome to Katona.
First, I try without the mic. Can you hear me? Okay. So, I'm very grateful for the organizers for inviting me to this excellent conference. But even more, I am grateful for publishing this very strong journal and organizing a community around it. And I'm very proud being a part of this community. Yeah, Janos pointed out that there is an error here. Somehow I didn't finish the sentence. Yeah. So I start with an old theorem of Sperner. The question was find the maximum number of subsets of an element set in such a way so that this is excluded. So one cannot be a subset of the other one. Actually, this was asked by Sperner in a number theory term that if you take square-free integer and then the subsets correspond to the divisors. Yeah, so this cross here should be red. Unfortunately, it's not really visible. So I can understand that in this country red is not a popular color anymore. Yeah, so it's easy to see that if you take all n-half element sets, then there is no inclusion among them. And so he proved almost a century ago that this is the best. You cannot have more. And of course it is sharp, and so this is exact maximum. This was generalized by Erdős. Still, the goal was number theory, that you don't allow a chain of subsets, where these are, of course, strict inclusions. Then, the best what you can have if you take k levels in the Muller lattice. And of course, then there will be no chain of length k plus 1, and here again this is sharp, and this is exact minimum. So Erdős had an impact on everything in combinatorics, and so I have a picture where he is working hard in my home. So now I will consider generalizations where the excluded patterns are expressed only by inclusion, because there are thousands of possible generalizations. So I will use the concept of a partial order set. A poset, everybody knows that for the one person who does not know, I repeat it. So it will be a set, and ordering is introduced on the set where at most one of these hold and it is transitive, and we call two elements comparable if one of these hold. And we will use this concept in two different ways. One is when the underlying set is the family of all subsets of an n-element set, and the ordering is the inclusion, and this is called sometimes Boolon lattice, but we will not use the lattice properties, only a partial ordered set. So this will be one usage. We will use small posets also for defining the conditions. So we will work in this set, and the condition will be given by small poset. So just how I will illustrate it. So this is the Hasse diagram of the poset. So these 2 points are not connected, although they are in relation, they are comparable, but it makes the picture too complicated. So this is actually the cube, the Hasse diagram of the Euler cube, and for Bn, I will use this picture, k minus first level, k level, and so on. So now I try to illustrate the Sperner theorem in these notations, these pictures, these illustrations. So it means that we choose these points in the Boolon lattice. These are subsets originally, and this waved line means that they are comparable. They are not in the Hasse diagram. So it's a path in the Hasse diagram. So this is forbidden because this would mean that this is a subset of this. And the question how many such points you can choose in the Boolon lattice avoiding this. And the answer of Sperner is that you take the middle level, all sets the middle level. So now the generalization, you fix a small poset and take the maximum number of elements in Bn in such a way that if you connect two points to sets, if they are in inclusion, so they are connected with a path in the Hasse diagram, then in this way it induces poset, and this poset does not contain P as a subposet. This is the condition, and this is the notation which stands for largest. So one more illustration. If P is this one, 4 elements where these are the comparisons, then we want to choose these points which should be red originally. So the red points in such a way that if you connect any two in inclusion, then you don't find this as a subposet. And this is also bad. This is also excluded because we are not looking for an induced copy, just a copy. So now the first example, I go back over.
Can you repeat the last sentence?
Sorry?
Can you repeat why the second one is also bad?
Okay. Because this is also an embedding of this in this way.
Well, P in the beginning is chain, and that also chain, right?
So this is a 4-element poset where these are comparable, are 3 comparisons. And if you look this path in this form, so you note only these comparisons, then this is like this.
The chain is always forbidden because the chain
Yeah.
contains everything.
The number of elements is, yeah. So that should be another. Sorry?
Chain is undirected, yes?
Undirected. No, it's directed in a way, but
Yes.
This one is.
so we exclude 4 elements in such a way that one is bigger than this one, and bigger of these 2, and this is bigger than this one. And in this one you find all these comparisons. So this is also forbidden. So if the poset is just two elements compared, then we get this question, and Werner answered long ago that this is the best. And in Erdős case, we forbid a path of length k plus 1 in subset form. Let me show you always. It always has a subset form. Subset form is a chain with a series of inclusions. Then the best is to take the k middle levels. Of course, you cannot have a chain of length k plus 1. So, third example is VR. You understand why I did not by V, because V2 would be just a letter V. So there is one element and R above it. Of course, they don't have to be consecutive. So it means in set form that the corresponding family is that there is a bottom element. All other sets contain it. The question, how many sets you can choose without this configuration? And let me show you a construction for V2. So it means that there are no free sets in such a way that one is included in two different ones. And so we learned from Sperner and Erdős that the full levels are very good. So we start with this full level. Of course, we can add something on the next level, say, but we cannot have all of them, because then the intersection of two such sets could be sitting here in the middle level, and that's a letter V. So we can have only a few of them. Namely, and this condition should be satisfied, that the intersection of any two is below the middle level. Then this will be also good. So we have now a modified problem, but it's not equivalent with the original one, so it's under the condition that we chose the middle level. And then, so find many sets of this side such that the intersection satisfies this condition. And this is an old problem of coding theory. This upper bound is trivial, and the lower construction is due to Graham and Sloan. So you can see that there is a difference here in the coefficient, factor 2, and this is unsolved since 1980. And so in this way, we were able to construct this much, because we had the full level plus, by this construction, 1 over n times the middle level. So that means we constructed in this way this match, this many sets, and we proved with Correa and Tomáš that this upper bound is good. But it's obvious that since this problem hasn't been solved, it's 1 or 2, it is kind of equivalent. It would be quite kind of equivalent to determine 1 or 2 here also. So that's still open.
In your lower bound, you also take a full level plus something. In your lower bound, take a full level plus something.
Yeah, the full level plus this one. And so I use this construction of Graham and Sloan to add this level. Sorry?
No, it's upper bound.
The upper bound is new here. So this is the lower bound is a consequence of Graham and Sloan. So
including the constant over its way. You have 1 plus 1 over n plus constant over n squared for the lower bound.
Well, yeah. Sorry, something is not clear.
So you get an extra 1 plus 1 over n plus constant over n squared.
That here, yes.
Yeah.
No, we don't have a construction, but this is a construction, and we can prove that it cannot be more than this one. But there is a gap between the lower and upper estimate.
But the construction is still.
Yeah, so I mean, we use just this construction. Full level plus we add this level using the construction of and slope.
But here you have 1 over n squared.
No, because here there is no 1.
1 over n squared.
And this is only this level.
Now look at your lower bound. You have constant over n squared. 1 plus 1 over n plus constant over n squared.
No, where is n squared?
This is not in here.
I see what you the error term.
Right. Because
It's
you
not in that construction. I think it is.
in the construction, you take things with a constant sum.
Yeah. It's not. It doesn't give this.
I thought. Okay, I'm not sure.
I think. No. I think it's exactly this one. I think.
Okay.
It is sharp. So this is we do not need this term here actually. I wrote it only here because we have the upper bar. Yeah. So we don't need it. Okay. Thank you for that. Okay. So and then quite recently we were able to generalize this for the general beads with analysis of the ponies. But again, we have this factor 2, which seems to be unavoidable until now. And then with Jerry Griggs, we solved this for n, and observed that the bounds are the same as for the beam. So excluding something more, so the condition is weaker, the result is still the same. Of course, the third term would be different, but the first two terms are the same.
Just to understand, what's that? What's the configuration?
N.
This one.
I thought it was self-clear. And actually, it's interesting if we continue with M, then we don't know if these constants are the same or not. How much the snake, it's not so interesting. Okay, so, but if you add one more here to the N, so we exclude only this one, which due to Jerry Griggs is called butterfly, then it becomes different. We can have the two middle levels. And we proved that this is the best. This is an interesting story that we proved this with the bonus, and then when we were done, we obtained a letter from someone. Someone asked from South Africa if this is known or not. And we said, yes, it is known since a month or two. And so Sanapul was the guy from South Africa, and he sent his proof. And both proofs consisted from two parts. And one easy and one hard one. And they exactly matched. So our easy part and his easy part gave a relatively short proof. But now there's a book proof by Gucci and Daniel Noy. It's really, really true. It became trivial. But that's a nice trick. Because both were participants of the International Mathematical Olympiad, so they are not so bad. And they also gave an upper estimate for every case, and they found an infinitely many series of posets where this is sharp. But of course, only few. I mean, infinitely many, but very few. And there are some improvements by Hong, Lin Chen, and Wei Chen Li. And so this is the asymmetric butterfly or ninja butterfly. And Abhishek Maduku and Kate Tompkins proved the same result. So it's even stronger, stronger result. I want to mention here is very interesting. So Hungary is not a typical place to attract foreign students from other countries because of the language and financial situation. But there's a small private university founded by George Soros, and it is basically our institute is doing the teaching there. And each year we have about 5-6 PhD students, and most of them decided that they are interested in this theory of extremal families, and they came to study in Hungary to this university. And this first result he has some more. From India, of course. Now, so until now we were always trying to get at least even not the main term, only the second term. But then some people realized that the main term it can be interesting without knowing the exact second term, and so they tried to solve it for all trees. The tree means for a poset, of course, it cannot, if it has more levels, it cannot be a real tree in the graph sense, but if the Hasselbalch is a tree. And Greeks and Indian solved it for two-level trees. That, so the main term is 1. So basically we can choose only the middle level. And Book, one of the excellent students of Benny Sudakov, proved a general form for every tree, and this is the height. Height means the length of the maximum pass, counting in the points. So then it means that you can choose HE -1 middle levels, then you cannot have a tree with height HT, and this is exactly the main term. So here, of course, they all get something for the second term, but it's too weak, so there's a big difference between the two sides of the second term. And so when I was giving a talk somewhere about the B problem, then someone from the audience, I'm sorry, I don't remember, I did write down, asked, what about this one? And I said, oh, well, I think our method should work for this one also. And so now, about 10 years have passed and it's still unsolved. So it means 4 sets in such a way that the intersection of these two contains 1, and the union is contained like this one. And of course you can choose the 2 middle levels. So the lower bound is trivial, but the upper bound is not trivial at all. So the first published result was this one, again a Russian name. And then it was improved by people in South Carolina. And then the report is now from Iowa, sorry. Iowa, and sorry, yeah, I don't know. No, okay. No, it was, no. Okay. So, it's an easier problem if we decide that the sets must be in the 3 levels. And then, of course, there are stronger estimates, but still unsolved. No, Yoshi is still not here. He's still sick. So, and of course, everybody conjectures that you choose some middle levels, asymptotically dispossessed for every, even for the diamond. And the first application of this type of theorems in other, of course, still families of subsets, but other problems using Hooke's theorem due to platforms and appeared in this journal. So now I want to start something new, very new, a different way of generalizing Sperner's theorem. So now we have a small poset P, and we want to find many copies of this poset in such a way that two elements, one from here, one from here, they are not comparable. So what is P? So this is an embedding of P, order preserving map, and there is an easy special case when first it's this the height again, and it's pretty easy to prove this upper bound for every P, but this is not sharp only if P can be embedded in this one. So if you take the top element and the bottom element, and you take the polar lattice between these elements, if the poset is within this, then this is sharp, because you can construct this many copies without comparable copies of in this way. So you divide the underlying set into two parts this way, and then take all half size sets here and add all subsets here. So they will be small copies of this, and they are not comparable. But this works only if so you construct this copies. If P can be embedded here, then it is sharp.
So again, when you say no comparable, means no element with one copy will be comparable. Is no element?
Yeah.
So not a corresponding, not a bijection.
No. So one here, they are not comparable. So this is a funny thing that you want to find the maximum number of these copies of this or this, the result is the same. You cannot do better than when you want to look for this. If you construct this one and then take path. So, small observation. So now I want to, I'm trying to have a conjecture. What could be the general result? So, if P star is an embedding into Pn, so one copy, and you take two elements of the embedding and a third element between in the polar lattice, which doesn't necessarily belong to the embedding, and if a D is incomparable with the elements of P star, then B and D are also incomparable in picture. So you have A and C are in, B is not, and D is not comparable with the elements of P star, then it cannot be comparable with this, because if it's comparable, then it's comparable with A also. And of course, same. So, as a consequence, so this is the convex closure of P star, because you cannot speak about the convex closure of poset itself, but in the case of embedding, of course, yes. And so you take everything between two elements. So the consequence is of this observation that if you take two incomparable copies of embeddings, then the convex closures are also. So we can consider, that's the conclusion, we can consider the convex closures instead. So this was the original problem. So more precisely, they are embeddings, P1 star, P2 star, and so on. And if you take the convex closures, they are also incomparable. And one can prove using the chains, counting the chains like Rubel's proof, asymptotically, this is, so I forgot to write here, these are the Q. So these are the Q stars, I forgot to write here. So this is Q star. And so the sums of this cannot exceed n choose n half. So I don't expect you to see this. I just play it. It's not hard to prove if you take all the chains going through.
What do you mean by asymptotically always? For large A?
For large N, yeah, for large N. So what is known about these extensions? So about these closures, it should be, of course, a complex embedding, which is P is a subposet of. That's obvious. So in other words, Q is a, how to say, superposet of P, and which has a convex embedding Qi star. So it's a bigger poset which has a convex embedding. That's the condition. So what we need really the minimum of this under this condition, because then you can say that n times this minimum size that is. So let me show you an example. So this is P, the excluded poset. I mean, no, we want to exclude the comparison. Okay, you understand. So we could do this. So because in some way, so if they are embedded, so if they are embedded, so then this will be we need something in between, and so we need this extension here, But this is not good because this is not embeddable in 3 levels because if they are on the next level, then the intersection of these two sets is either this one, not both. But you can do it in 3 levels, but then you need more points here. So this is not good, but this is good. So this is a good extension of and Q is this level is easy to see. So this is the complex embedding number. Of course, the P is the smallest such Q, which is the super poset of P, and Q already has a complex embedding. And then I claim that this is asymptotically true. Then this will imply this inequality. So we have basically M is at most this over CDM P. And so there's a non-trivial construction, actually 2 non-trivial constructions because we solved it independently. It is difficult to decide within a month or week or whatever. So it was a little bit surprising that we have the exact asymptotic solution for all P's, like in the other problem. But I mentioned earlier that if P can be embedded into this one, then we have an exact solution. It looks so different. They are not contradicting each other. No, because this is equal to, asymptotically equal to this one. You always divide by 2 when you take both on it from this to here. And this is the embedding number. So this will become this one. But when you have the asymptotic solution, you are still curious about the exact solution. Of course, we had, especially because we had the exact solution for a large class of posets. So try to do for this one. So suppose that n is even and they are divided into pairs. The ground set, the underlying set is divided into pairs. And take 2I elements here, and this is the red pair, different for here. Yeah, so this is red, and this is blue. So the difference is here 2, so we don't count this. So this is, and now we take this many elements out of this part. So this many elements out of this. So it's smaller than half of smaller than. And so this will give now. Yeah, so okay. So these are all in the set, and we have this many sets. So all together, so they are not in the set. The red ones are not in the set. Only all of these, and half of this many out of this place. So all together, it will be this plus this, which is n half minus 1. So these will have this size, these sets. And then add, so this became blue now, And so we add this one, then we get an n-half element set, which is a superset of this one. And then flip it, so take this inside and remove this one. Then we get this, and of course we don't take the set when both are in. Then we forget about this one because then it could be bad. And it is easy to see. I don't expect you to see immediately, but few cases that this will be, if you take it for all I, that then they are incomparable. So the number of these sets where I is fixed will be this much. So we take out of this many that we take all these, and then we add up for I equal to 0. I didn't write here the top because it depends on divisibility of its form. That's argument. And we conjecture that this is the exact test, and it works with some modification integer part for odd and also. So this is my impression about Moscow winter. And finally, conference announcement. There will be a conference in July 7th to 11th. And you can find information. At this moment, very small information, but it will grow later. And so one of the celebrated persons is sitting here. They are all getting old. I have to recall saying of Nogam, I think it was Lova's 60th birthday, that we realize that each time younger and younger people turn 60. Thank you for your attention.
Any questions, please? Maybe I have a question then. What about the iteration problems? So these are external problems and maybe the Dedekind's problem also is generalized in some way here in some results.
We didn't consider it. I don't know.
Are you aware of any progress in this area?
No. So you know the number of Spanner families that are some well-known results like Korshunov and Saposhenko, but I don't think there is anything even in this direction. Number of Erdős systems, I never heard about the papers following.
So three papers by concerning the D-sets.
Yeah, that's in the paper. Oh, I should know this.
Okay. Any more questions? Okay, then we have a 5-minute break. 18 minutes.